We have data that is discrete and we have data that is continuous. So when we have the counts, we learned that we were dealing with data that is discrete. You're going to use discrete probability distributions to find probabilities. For example, the probability that X is going to take a value. That's what we did in the last chapter. So we can use, for example, a probability histogram. A probability histogram to do that. For example, the probability that X is going to take this value here is going to be just this bar here, either the area of this bar, because when you are dealing with the probability histograms, the area is going to be the same as the value that is on the y-axis. So if you read here 0.4, then that means that the area within this rectangle is also 0.4. But this is a discrete probability distribution, so you can only get values of probabilities for given values of X, discrete values of X. So, and on the other hand, when you have measurements, we know that our data is continuous. So we're going to use continuous probability distributions to find probabilities. But this time we're not going to be able to find the probability that the X takes a single value. The only thing that we can do is we're going to find the probability that the X is in or within an interval. So for example, the probability that X is between a value A and a value B, a measurement A and a measurement B. For that, we're going to use curves. Now, we're going to use what we call probability density curve. This is going to be a probability density curve. And if you want to know the probability that X is between A and B, then we're going to need to measure this area here, and the area is going to be related to that probability. So that's what we're going to cover now in this chapter. This chapter is for continuous probability distribution. The most important one is going to be the normal distribution. So in your book, on page 293, we have the normal distribution. So we're going to use then, instead of histograms, we're going to use curves. Curves is just a generalization of a histogram, because as long as you make the width of every bar very, very small, then you're going to get, at the end of the day, a curve. So we're going to be working with curves like this one. So that's what we're going to do. So the most important thing is the meaning of the areas of those curves. So as I mentioned before, the curve is going to receive a name. The name is a probability density curve. On page 295, we have just here a summary indicating the main properties of those probability density curves. The most important one is that the area under the entire curve is going to be equal to 1. Then the area under the curve between two values, A and B, has two interpretations. So anytime that you see an area between value A and value B, you can say that that area represents the proportion of the population whose values are between A and B. Or the other interpretation is that the probability that a randomly selected individual will have a value between A and B is going to be the area under the curve. So we're going to solve some problems dealing with those properties, but before, I'm going to write here the summary. This is good for our notes, because we're going to need this later. We're going to apply these things a lot of times. So we have a probability density curve. Again, this is just for continuous probability distributions. So the first thing is the area under the curve is equal to 1. And then the area between A and B is you can say that it's going to be the proportion of the population whose values are between A and B, or is going to be the probability that a randomly selected value or individual will have a value between A and B. So you have here then your probability density curve. The entire area under the curve, the total area is going to be equal to 1. And if you have just a piece of the curve and you have values A and B here, then this area, the area is the proportion of the population between A and B, or the other interpretation is that the probability of a value being between A and B is going to be that area under the curve. So this area is just a proportion. So if this area is just 0.3, you can say that 0.3 of the population is between A and B, and the rest is outside of that interval. Or what is the probability that X is going to be between A and B? Just measure the area. So we're going to solve a problem where we're going to apply these principles related to probability density curves, and then we're going to move on to our normal distribution, which is the most important one that we're going to learn in this semester. So let's see, we're going to work on example 7.1. Example 7.1 is on page 295. So we have here the example. I'm going to show you the problem. So following is a probability density curve for a population. So we have that curve. It doesn't matter that the curve is not symmetric. It's just a curve. The only important thing is that the area under this curve is going to be 1. It can be less than 1. It can be greater than 1. It should be 1. And then we have 4 questions. What proportion of the population is between 4 and 6? So these are the values that any individual can take within that population. And these are just measurements of the Y values corresponding to this curve. So these measurements are not going to tell us anything. So we don't use this information. We use just areas under the curve. So for example, what is the proportion of the population between 4 and 6? Then we're going to solve this problem. Then we have 3 more problems. So let's start with the first one. So we have example 7.1 here written for you, for your notes. So this is on page 295. So I have my density and my probability density curve in this way. So your book says that this area is 0.16. So the first question, what proportion of the population is between 4 and 6? So the proportion of population whose values are between 4 and 6 is the area under the curve within that interval, or bounded by that interval. So what is the area between 4 and 6? The area under the curve is 0.16, so that's the answer. So 0.16 is the proportion. Now, the second question, if a value is chosen at random from this population, what is the probability that it will be between 4 and 6? So now the question is, what is the probability that x is going to be between 4 and 6? We write x greater than or equal than 4 and less than or equal than 6. So what is the answer? Is again the same thing, the area under the curve between 4 and 6. And what is that area? 0.16. So you're going to have two ways to interpret the area under the curve. So you're going to need to read carefully your problem. If they are asking you about the proportion of the population between two values, is the same as if they are asking what is the probability that you pick a value and the value is going to be between 4 and 6. So now the third problem. What proportion of the population is not between 4 and 6? So you know the proportion uh, between 4 and 6 is 0.16. Then the proportion not being between 4 and 6 is going to be 1 minus 0.16. Why? Because we said that the total area under the curve is 1. Then if the proportion between 4 and 6 is 0.16, then the rest of this area is just 1 minus this area. So you're going to need to subtract 0.16 from 1. So the answer is going to be just using our calculators, and you're going to find that the answer is 0.84. Now, the final question. If a value is chosen at random from this population, what is the probability that it is not between 4 and 6? So this is the complement of question B. So you know that the probability that the value is going to be between 4 and 6 is 0.16. So then the complement of this is the probability of x not between 4 and 6 is going to be 1 minus 0.16 again. So it's going to be 0.84. So those are the interpretations. Either you are talking about proportions of individuals being in a certain interval, or the probability that one individual is going to be within that interval. So that's what we need to know about the interpretation of these areas. So let's continue with our analysis of this. So we have two kind of problems that we're going to solve from now on. So either you're going to have, so case 1, and this is a general thing for the rest of the semester. So this is something very important. This is a parenthesis. So you're going to have different kinds of curves. So we're talking about continuous probability distributions in general. So we are talking, there are 3 different cases. So we have, for example, the normal distribution. We're going to learn about that in a minute. The normal distribution. we're going to have something similar to this one, but a little bit farther. It's going to be the student T distribution is also symmetric. And then we have a non-symmetric curve, something like this. And this is going to be the chi-square, and this is chi-square distribution. So our case one for any continuous probability distribution, and there are more. These are only 3 examples that we're going to use very often in this semester, but there are more. So case one is you are given x, and then you're going to find the probability of x being within an interval. In other words, given x, what is the area? So usually we're going to work with the area to the left. Most of the books have tables. So your books give the area. So given a value of x, they're going to give you the area on the left. It doesn't matter whether it's on the right part of the curve or on the left part of the curve. In all cases, what you are given is the area on the left. So to find the area, on the left of x, you're going to use a p function in R. In R, use a p function. I want to emphasize this little p here. So, for example, for the normal distribution, we're going to use p norm. For the student t distribution, we're going to use p t. For the chi-square distribution, we're going to use p chi-square. So it's going to be very easy. Everything from now on is going to be very repetitive. So we're going to study different cases where you use a normal distribution, other cases where you use a t distribution or a chi-square. The only thing that you're going to be changing is the function. If you are computing areas, you use a p function. If you are in the other case, the second case, is when you are given the area and you need to find x. So that's the opposite case, the inverse case. So case 2 is going to be the inverse case. So you are given the area on the left to find x. So it's totally the opposite. First you're given x and find the area to its left. Now you're going to be given the area and you need to find. So again, the normal distribution, the t distribution, or the chi-square distribution. In those cases, you are given now an area. This is given, and you want to know this value here. So maybe you are given this piece, and you want to know this value here. What is the value of x? Or you are given all this area, and you want to know this value here. So to find these values that we're going to call quantiles. So this is going to be a quantile, and quantile. To find quantiles, so in R, you're going to use a Q function. So you use a Q function. So you are given this area and you find this value, you're going to use Q norm, or you're going to use QT or you're gonna use Cwk7a. So P functions, with P functions you find areas or probabilities. So let's summarize here. With P functions, we find areas under the curve, which are just probabilities. So, for example, p-values, we're gonna find p-values in the last part of the course. And you use Q functions to find quantiles given the area under the curve, which are also known as, we're gonna find later, critical values. We're gonna use critical values to make decisions. We're gonna use p-values to make decisions. So you start becoming familiar with this kind of terminology. So we're gonna start now working on or with the normal distribution. So let's see. This is on page 296. So let's check page 296. Yeah, on page 296, we're gonna start working working on the normal distribution. So let's see. So the normal distribution, then the normal distribution is on page 296, and we're gonna have two kinds of normal distribution. We're gonna know about the standard normal distribution. We're gonna know about the normal distribution, the general one, the normal distribution. What are the differences? For the standard normal distribution, the mean is always 0. For the normal distribution, the mean can be different than 0. The standard deviation for the standard normal distribution is going to be 1, and for the normal distribution is going to be different than 1. So we're going to use x here to find probabilities or areas, probabilities. So for example, we're going to use p norm. We're going to provide the value of x, we're going to provide the value of mu, and we're going to provide the value of the standard deviation. If you use this command in R, what you're going to get is the area to the left of x. That is what you're going to get. For the case of for the standard normal distribution, instead of using x to prevent confusion, we're going to use z, the z-score, to find probabilities. And you know that the z-score is just x minus mu over sigma. So the way that you're going to find the probabilities is just going to be you're going to use p norm, and you're going to use just the z-score. So this is very, very easy to work on. So, and then with p norm of z, you're going to get the area to the left of z, the z-score that you found. So finally, I just want to mention, for completeness, remember when we work with the binomial distribution, we have an equation for p of x, which is something at n z r, and then we have p to the x and 1 minus p to the n minus x. So it was a very complicated equation, but we said that we didn't have to know about the equation. The same thing with this function. So we have the standard normal distribution, and the normal distribution here, the mean is 0, the standard deviation is 1. Here you just have the mean and the standard deviation to be any values, and there are equations for this curve. So if you look at more advanced books on statistics, you're going to find that the equation for this curve is just f of x is going to be 1 minus sigma times the square root of 2 pi times e to the negative 1/2 that multiplies x minus mu over sigma and square. And for this one, the function for this curve is just going to be 1 over the square root of 2 pi e to the negative 1/2 z squared. So it's simpler, this equation, than this one. But anyway, we don't need to deal with this equation, because to find areas, so to find areas using the equations of these curves, these density curves, we have to use integrals. If you take math 20 or math 18 here, you're going to see that the area under the curve is going to be an integral between a and b of that given function dx. So you don't need to do that. You either use tables. So instead of using integrals, you can use tables that are in your book, in the appendix. You can use your Texas Instrument 8384 if you are familiar with that, or you can use just language R, and we're going to use the P functions that I just talk about a little bit about that a little bit later ago, a little bit ago. So these are just the information that you need to know about the normal distribution. That we have the standard normal. These are the conditions, and we have the general. So the properties, I'm not going to copy everything that is in your book. You can just check your book on page 297. We have the properties for the normal distribution. So the normal distribution have one mode, that's the maximum value. They are symmetric around the mode, and also the mean, the median, and the mode are the same. So it's the same value. If you find the mean equals to something, that value is the same for the median, and is the same for the mode. And then these normal distributions follow the empirical rule. The empirical rule is just you can know the areas for certain values of the standard deviation. So for example, in this graph, in this plot, you can see that you have the mean here. If you subtract one standard deviation from the mean, you get here. If you add one standard deviation to the mean, you get here. So between one standard deviations, you're gonna get 68% of the values falling in this interval, or the proportion of the population being 68%. That is within one standard deviation on both sides of the mean. If you subtract two standard deviations, you're gonna get to this point, and if you add two standard deviations to the mean, you're gonna get to this point. So you're gonna get 95% of the values within two standard deviations, and finally, within three standard deviations, you're gonna get 99.7 of the values. That is gonna be the proportion or the probability when you are within three standard deviations from the mean. So I think it's the time to work another example. So we're gonna work example 7.2, and I think later you're gonna have some work to do. So let's see. We have example 7.2. That example is on page 298. So, and here you have the problem. You want to find the area that is going to be to the left of a z-score. So we're going to use the standard normal distribution. So in this case, they are showing you how to use a table from the appendix of the book to find the area. So you have here the standard normal distribution. You are given a z-value of 1.26, is here, and they want to know what is the area to the left of this z-score. So if you use tables, if you just want to use tables, just follow this example. Otherwise, we're going to use just R. So in this case, we need to find the area to the left of z equals 1.26. So we have z equals 1.26, and we learned that the area to the left, so the area to the left is going to be just p norm of z, so p norm of 1.26. So with R it's going to be very simple, the thing that we need to do. So let's go and start working on our R console. So we need to type p norm of 1.26, and we're going to get the area. The area is just 0.89, 61, 65, 3. So that's the area to the left. If you check the book, you're gonna see that the area that they found is just at the intersection of these two yellow stripes, so it's 0.8962. So, or you just use R and you get the result. So now we're going to work the next example. So example 7.3 on page 298. We're going to find the area to the right of z equals negative 0.58. So that's example 7.3. It's over here, and they are suggesting to use the same table to find the area, because tables in this book give you the area to the left. So we need to do just an extra computation. We know that the area to the right is going to be 1 minus the area to the left, so it's going to be 1 minus p norm of the z value that is given. So in this case it's 1 minus p norm of negative 0.58. So that's what we're going to do now. So again, we need to use R, your Texas Instrument 8384, or tables. So 1 minus p norm or negative 0.58. So we're gonna get 0.719427. So that's the answer for this problem. So let's continue working on more problems. So now we're going to find the area between two values. So that's example 7.4 on page 299. So now we're going to find the area between z equals negative 1.45 and z equals 0.42. So now that's what we want to do. So we're going to find the area between z equals negative 1.45 and z equals 0.42. So if you have a curve, you have the standard normal is always 0 here, then you have negative 1.45 here, and then you have something like 0.42 here. So we want to know this area. So now we have an upper z and a lower z. So the area in between, I'm going to write area in between is going to be P norm of the upper z minus P norm of the lower z. I run out of space here, lower z. So in this case, it's P norm of the upper is 0.42, that's the upper z, minus P norm of the lower z, which is negative 1.45. So we use R to find that information. So now we need to write P norm of 0.42 minus P norm of negative 1.45. So the area is 0.58. So we are finding areas, but remember those areas are going to be probabilities later in the coming problems. So now you're going to start your assignment. This is the first part of the assignment for this lecture. So we're going to have a couple of more breaks later to get more problems for your assignment. So the first part is that you're going to go and check section 7.1 exercise set on page 307, and you're going to work 3 problems: 24, 26, and 28. And remember, solve the problems and then you take screenshots, and you're going to need the screenshots later to get your PDF file. So we're going to start with 24. Okay, there are a lot of problems here that you can use to practice, right? Because you are given curves and you're given the values of z, and you find the areas that I are indicating here. But the problems I'm giving you are the following. 24 is here. So you're going to find the area under the standard number curve to the left of, and you're given 4 values. So get the area to the left of those 4 values. So these are 4 independent problems. So then 26, now you're going to find the area under the standard normal curve to the right. So remember, area to the right, you need to do a subtraction to get the difference. And again, you have 4 values of z, so you're going to get 4 areas. And then finally, problem 28, you're going to find the area between 2 values. So you are given the lower limit and the upper limit. So with those boundaries, you're going to find the area in between. So that's the first part of your assignment. So now we're going to continue with our section 7.1. Now we're going to work on the inverse problem. So given an area, we're going to find now the corresponding quantile. In this case, since we are using the standard normal distribution, that quantile is just the z-score. So we're going to find a z-score corresponding to a given area, and that is described on page 301 of your book. So we're going to start right away with the example 7.7. We already know that we're going to use a Q function because now we're going to find a quantile given an area. So example 7.7 is here. So again, you can use tables, your text as instrument, or language R to do this computation. So we're going to start with this problem, with this example on page 301. And the problem says use table 8.2 to find the z-score that has an area of 0.26 to its left. So they say use the table, but we're going to use language R. So the problem then, example 7.7, we're going to find, that's on page 301, we're going to find the z-score, that has an area of 0.26 to its left. So what we're going to do is we're going to use a Q function. So we're going to use Q norm to find the z-score. You use Q norm, but we need to provide the area to the left. In this case, that's the area that is provided. So the area to the left is just 0.26. So let's work this in R and let's see what we get. So our console is here. So I'm going to type now Q norm. So it's very important that you don't mix up these functions. Now it's Q norm instead of P norm. Q norm of 0.26, which is the area to the left of this z-score that we're going to find. So the z-score is negative 0.6433. So that's the solution for this problem. So if you are using just a table or you want a visual representation of what we are doing, is just the standard normal distribution. We have 0 here, and we have an area that is given. They are telling us that this area is 0.26, and we want to know this z-score. What is that z-score? So we use the Q norm function. So now we know that this z-score is negative 0.64. So now the next problem that we're going to work is going to be problem 7.9. So problem 7.8 is just the same problem as before, but using technology. So they are showing you how to use the text as instrument to get that z-score, or use language R. So now for example 7.9, they show you how to use a table to find the z-score that has an area of 0.68 to its right. So now it's a different area than the one that they are providing. So let's write here example 7.9 on page 302. So now we're going to find the z-score that has an area of 0.68 to its right. So you have your 0 here. 0.68 is more than half of the area, so is going to be something like this. So we know now this area. This area is 0.68, and we want to know this z-score. So when you have the area to the right, then you're going to use the same function, qnorm, but we're going to subtract the area to the right from 1. So that's what we need to do. So we're going to get qnorm of 1 minus 0.68. In that way, this difference is giving you the area to the left. That is what you need to use qnorm. So we're going to get now the answer by using language R. So let's see. We're going to get qnorm of 1 minus 0.68. So this is negative 0.467698. So now we know the corresponding quantile for the given area, and this negative 0.46. So finally, we're going to solve one more problem. That's example 7.11. Example 7.11 is on page 303. So let me show you the problem first. So we have here example 7.11. So the question is very simple. We're going to use the table, your Texas Instrument, or language R to find the z-scores that bound the mirror 95% of the area under the standard normal curve. So now we're going to find boundaries, two boundaries, and the area in between is 95% or is 0.95. So let's write this problem here for our notes, and then we're going to be able to work on that problem. So this is example 7.11 on page 303, and we're going to find the z-scores that bound the middle 95% of the area under the standard normal curve, under the standard normal curve. And this is important. They are talking about the standard normal curve because the values might be different if you just talk about the normal curve. So 95%. So we have the standard normal curve with 0 here, and now we have 95% of the area. So we're gonna do this symmetrically. So let's say that these are the boundaries. So this is the lower z, or z1, and this is the upper z that we're gonna find, or z2, and the area in between is, this area is given, the area is 0.95. So to find these values, what we need to know is the area to the left in each case. So for z1 and for z2, so first we need to find these areas. So this is, I need to highlight better this. Okay, I have my pencil here to be able to see the difference. So this is the dark area. That's what is 95% of the total area. I'm doing this for you to see the little pieces that are not dark. It's just two pieces here. There are two pieces here. So this little portion here under the right tail, and the little portion under the left tail. So we need to find these values first, because this is what we have been using in the previous problem. So what are these values? So these values are going to be half of the difference between 1 and 0.95. So the difference, so the area outside of the region. So let's say outside area, we're going to divide that area by 2 because this is symmetric, so the outside area is going to be divided by 2. So what is the outside area? The outside area is just 1 minus 0.95. So the outside area is 0.05. So that's the outside area. So we're going to divide this by 2, and that is going to be the little part that corresponds to these little areas under the core, the little pieces. So let's start with Z1. With Z1, I just need the area to the left. So Z1 is going to be Q norm, and the area to the left. So the area to the left is just the little portion. It's just 0.05 divided by 2, because that's the outside area. 0.05 divided by 2. That's the area for the first one. Then we're going to find a value in a minute. Then for the second z-score, now I have the area to the right, which is also 0.05 over 2, but that's an area to the right, so we need 1 minus the area to the right. That's what we do when we have the area to the right. So Z2 is going to be Q norm of 1 minus 0.05 over 2. The area to the right, this little piece, is also 0.05, which is the outside area. Outside area. And this area divided by 2 is this little piece here. And the other 0.05 over 2 is the other little piece. So let's just do these computations to finish our problem. So let's see. Let's move on to our R console now. So I have a Q norm of 0.05 over 2, and this is negative 1.95, 9964, and then the other one is going to be Q norm of 1 minus 0.05 over 2, and that is 1.95, 9964. So let me show you the computations. So we have here, so this value is negative 1.95 and this is positive 1.95. So this is also interesting because we are working with a curve that is symmetric with respect to the center. So that's the reason these values are just opposite in sign. So finally, I'm going to give you for this section the last part of the assignment, and then we're going to continue with the next section to complete our lecture today. So the assignment is from 7.1, exercise set on page 307, and you're going to work now problems 32, 36, 39, 40, and 42. So 5 more problems to finish this section. So the problems are here. So you just need to look within this section here. 32 to 42. To finish this section, we're gonna work on, to finish this lecture, we're gonna work on section 7.2, which is applications of the normal distribution, and it starts on page 308. So we're gonna start using the same R command that we used in the last section, But now we're going to have problems that are more elaborate in terms of we need to read carefully what they are asking, what they are providing to be able to solve our problem. So the only thing that we need to know is that if you're going to use the standard normal distribution, then you need the z-score. If you don't remember, the z-score is just x minus mu, the mean mu, over the standard deviation. So we already know this definition of the z-score. I'm going to write it down again in our notes. And another thing that you might already know is that the z-score follows a standard normal distribution, something that I have mentioned many times before. And also that the mean for the standard normal distribution is 0. So values below the mean are negative, and values above the mean are positive z-scores, because we are saying that the mean for the standard normal distribution is 0. Also, the z-score is just a measure of position, something that we learned in previous chapters, and it's just indicating how many standard deviation the original value is above or below the mean. So to the right or to the left of the mean. So you only need to know this formula if you're going to use the standard normal distribution, because you can use directly the normal distribution to solve the same problems that we're going to solve now. But following the book, we're going to do the extra step of finding the corresponding z-score, and then you use tables, your Texas Instrument or language R to find the corresponding probability. So I have here that you only need to remember that the z-score is just x minus mu over sigma. And you can check on page 308 the properties and the meaning of the z-score. So we're going to go now example 7.13. Problem 7.13 is on page 310. So this is the problem. We're going to start now having a word problem, and we're going to use the same tools that we already know from a previous section. So the thing from now on is that we need to read very carefully the problem. We need to find keywords in this problem to be able to say that we can use the normal distribution. Otherwise, we might be doing assumptions that are not allowed. So example 7.13 is about the following. A study reported that the length of pregnancy from conception to birth is approximately normally distributed. So the first thing is they are talking about the length of pregnancy. So they are talking about continuous data. You cannot say that the length of pregnancy can be 9 months or 8 months or 7 months. So there are values in between. So that's a continuous data. That is going to be a continuous variable, random variable. So from conception to birth is approximately normally distributed. This is the second key component of the problem. They are telling you that the variable is normally distributed with mean mu equals to 72 days and standard deviation sigma equals 9 days. So now the question, what proportion of pregnancies last longer than 280 days? So that's the problem that we're going to solve now. We need to start first learning that we are talking about continuous data, that we're going to use the normal distribution because they say that the population is normally distributed. So that means that you can use either the normal distribution or the standard normal distribution. The standard normal distribution, or you can use the normal distribution. So if you use the normal distribution, you only need to know mu equals to 72 and sigma equals 9 days. If you are using the standard normal distribution, you know that you have the mean 0 and the standard deviation 1. So they are talking about the proportion. So we want to know the proportion of pregnancies lasting longer than 280 days is equivalent to finding the probability that X is greater than 280 days. So you can find this directly by using the normal distribution, because you know that the normal distribution, when they say that the pregnancy lasts longer, they are talking about um, an area to the right, because they say longer. So X is greater than, anytime that you have X greater than, this is the area they are talking about. That's the probability that we want to find. So it's going to be 1 minus the probability that X is less than 280. So the area to the left, and we know that we can find that by using P norm. P norm giving X, mu, and sigma. So it's going to be 1 minus P norm of X. X is, for this problem, is 280 days. 280 days. That's the question. The mean is 272 days, and the standard deviation is 9 days. That's one way. The other way is that we need to find Z, the Z score, if you use the standard normal distribution. So the Z score is going to be X minus mu over sigma. So our Z score is going to be, in this case, 280 minus 272 over 9. You're going to need to use parentheses to prevent mistakes. If you do these operations, you're going to find that the Z-score is 0.89. So when you are using the standard normal distribution, you need to write this in terms of Z. So you're going to write that the probability of X being greater than 280 is also the same as the probability of Z greater than 0.89. Again, you're going to need to use 1 minus P norm, because this is the area to the right, and you only need to use the Z-score, in this case 0.89. So when you use the Z-score, is directly. When you use the X value, you need to incorporate in P norm the mean and the standard deviation. So let's do that. Let's see whether we can get the same value for both. Otherwise, I might be missing something. So let's check. So first, I'm going to confirm that 280 minus 272, you use parentheses for the numerator, divided by 9 is 0.8889. Okay, 89. So let's start with using that Z-score, 1 minus P norm of, in this case, is going to be 0.8888 6 times, and then A9. So I'm going to get a probability equals to 0.1870. And if we use the other way, so instead of computing the Z-score, you can use directly the value of X, 280, the value for the mean, and the order matters. So you need to write this in the proper order, and the standard deviation 9, and we get the same value. So that's the solution. So that's the probability that a pregnancy is going to last longer than 280 days. So that's our example 7.13. So we have here the results for this program. So now we're gonna work another problem. We're gonna work example 7.15. So problem 7.15 is on page 311. So let's see. Problem 7.15. So we have now, we're going to be given two values now. So let's see. So the length of pregnancy from conception to birth is approximately normally distributed with mean mu equals 272 days and standard deviation sigma equals 9 days. A pregnancy is considered full term if it lasts between 252 days and 298 days. What proportion of pregnancies are full term? So now we're going to use the same population as before. So let's just use the same values as before for sigma and for the mean. So this is going to be problem. This is example 7.15 on page 311, and we know that the population of pregnancies has a mean equals 272 days, standard deviation 9 days. And now we have that the full pregnancy is between 252, that's the lower limit, and 298, that's the upper limit for a full pregnancy. So this is a full term pregnancy. So the mean is here, 272 days. So now we want to know what is the proportion between x 252 and x equals 298. So that's the proportion. So the proportion of full term pregnancies is going to be equal to the probability that x is between 252 and 290 days. So we can use directly the function p norm of the upper value 290a with mean 272 standard deviation minus p norm of the lower value 252, 272 the mean, and 9 the standard deviation. That is one way. You can also work with the z-scores, so we need to convert 252 to a z-score and 290a to another z-score. So how do you do that? You know that the first z-score is going to be 252 minus 272 over 9, and the other z-score is going to be 290a minus 272 over 9. Once we get these values, we're going to use p norm of the upper value minus p norm of the lower value to compute again the same thing, the probability that x is between 52 and 298. Okay, so let's find first the corresponding z-scores. So the first z-score is going to be negative 2.22, and the upper is going to be 2.89. So then the probability of having this inequality satisfied is the same as z being greater than negative 2.22 and less than 2.89. So, and this is going to be p norm of 2.89, which is the upper value, minus p norm of the lower value, which is negative 2.22. So let's do these operations. We should get the same answers by using any of those methods. It's going to be up to you, the method that you follow. I'm giving you both methods because there are some students that are repeating this class and they are familiar with computing this course for any problem involving the normal distribution. And the students that are learning for the first time statistics, they can use the simplified way, which is just using the p-norm function with x, mu, and sigma. So, and let's do that. That is the simplest way because you don't need to compute any z-score. So you just write the upper value, the mean of the population, the standard deviation, and then you subtract p-norm of the lower value to 52. Again, the same standard deviation, the same mean and the same standard deviation. So that is going to be the answer using the values, the original values, or you can use the z-scores that we compute in the second part. So the z-score for the upper part, the upper z-score is 2.89 minus the z-score, the lower z-score is going to be negative 2.22. So in any case, we get very similar values. In the second case, now I'm using the rounded values as there is in the discrepancies, the minor discrepancy, but the answers are the same. So we have 0.98, 49, 328 for the using the just the x values and mean and the standard deviation, or 0.98, 48, 644 when you use the z-score. So again, two ways to solve the same problem. It's going to be up to you, the one that you prefer. So that's the second problem. Now we're going to work on the opposite case. So when you are given an area, so the next problems are going to be given area, given the area, then we find the z-score, and then we find the x value. So you can follow again two routes. In one route, you're gonna use the area to the left to find the corresponding z-score. So this z-score is obtained by using Q norm of the area to the left. Don't forget this. If you're given the area to the right, you need to subtract from 1. So if you are giving the area to the right, then the z-score is going to be Q norm minus Q norm of 1 minus the area to the right. Once you have the z-score in both cases, you're going to use the same formula to find x. X is going to be just the mean of the population plus z times the z-score. Or the other method, if you are given the area to the left, you can find directly x by using Q norm. You're going to provide the area to the left, but also the mean and the standard deviation. Or if you are giving the area to the right, you're going to find x by using Q norm 1 minus the area to the right, comma, the mean of the population and the standard deviation. So these are the two ways to solve the problems that we're going to have now. Now you're going to have the area and you're going to need to find x at the end is what we need. Two routes. You find z and then x, or you go directly from the area to x by using the second method. So let's work on the next problem. So the next problem is going to be example. Let's see, we have example 7.17. So let me find problem 7.17. It's on page 313. So let's read the problem. So in that page, you also have steps if you want to use a table. So this is a little bit more complicated when you use a table and you start with an area and try to find the corresponding quantiles. But if you want to do it, just check page 313. So let's read example 7.17. So let's see. Mensa is an organization whose membership is limited to people whose IQ is in the top 2% of the population. Assume that scores on an IQ test are normally distributed. Again, this is a key component. The scores, the IQ scores are normally distributed with mean mu equals 100 and standard deviation sigma equals 15. So what is the minimum score needed to qualify for membership in Mensa? So let's have here our problem now. So the population of IQ scores. So we have a population of IQ scores, which is normally distributed. If they don't say that in the problem, you cannot do anything. You need to do other things, but don't use the normal distribution. So normally distributed with mean equals 100 and standard deviation equals 15. That means that you have a curve like this. So this is the population of IQ scores. The population is over here. So mu equals 100, sigma equals 15. So the top 2% of the population can get a membership with Mensa. 2%. What is 2%? 2% is just 0.02. So 0.02. This is the area. This is the proportion of the population that can get membership with Mensa. So they are going to be able to belong or to get a membership with Mensa. So we want to know this value of x. What is this value of x given an area to the right? We already have a formula. We know that it's going to be Q norm of 1 minus the area to the right, and we're going to need to provide the mean and the standard deviation. So that's one way to do the problem. If you already took this class before, you're going to need to use the z-score. So we're going to follow a different route. So we're going to find the z-score by using Q norm of 1 minus the area to the right. And then we're going to use the formula x equals mu plus z times the sigma, the standard deviation. So let's do both. So this is one way. or the other way then is, this is one way, or the other way is this one. So let's start with the first one. So just x is going to be just q norm of 1 minus 0.02, that's the area to the right, comma, 100 is the mean, and 15 is the standard deviation. The other way is that we're going to find our value for z is going to be just q norm of 1 minus 0.02. So let's do that. Let's use R to do these computations. That is going to be the last problem that you're going to have. No, we have one more problem, and then you have assignments. So first, let's find x directly. Q norm of 1 minus 0.02, comma, 100, comma, and 15. So when you use this way, you're going to get directly 130.8062. Now, if you use the other way, we're going to find first the z-score, which is 1 minus 0.02. So the z-score is 2.053. So the final step is we're going to find x by having the mean 100 plus the z-score, which is 2.053749 times the standard deviation, which is 15, and we're gonna get again 130.8062. So let me just copy that for our notes. So now we have from here we now get x equals it's going to be mu plus z times sigma, which is just 100 plus 2.0453749 times 15. So we get x equals 130.8062. So these two values are the same and the routes are different. So what is the value? You round up. So 132 is the minimum IQ score to get a membership with Mensa, to get a Mensa membership. So that's the problem. So we're gonna work one more problem. This is example 7.18 on page 313. So let's read the problem. The problem is here. So let's try to understand first. So they say IQ scores have a mean of 100 and a standard deviation of 15. So we already know that because that's. So we're gonna use technology to find the 90th percentile of IQ scores. So in other words, we're gonna find the IQ score that separates the upper 10% from the lower 90%. So percentiles, we're gonna use the standard normal, or we can use the normal distribution directly. So let's work on this problem, and then you're gonna have some 3 or 4 more problems to complete your assignment for this lecture. So what we have here is, again, the population of IQ scores. So population of IQ scores. We know that the mean is 100 and the standard deviation is 15. Now we are looking for a value, an x value here. We are looking for an x that separates. So this is going to be the 90th percentile because you have here 90% and you have here 10%. So that value separates the lower 90% of the population from the top 10%. So what is the process? Now we know the area to the left, so you're going to use directly Q norm of area to the left, mu and sigma. So your value of x is going to be Q norm of 0.90. Then you write here 115. Or you use the other process. So you find the z-score. Again, with Q norm, the area to the left is just the area to the left is just 0.90. And when you find this z-score, you're going to find x as z plus, no, mu plus z times sigma. Okay, let's do that now. And with that, we're going to finish our lecture today. So we have first Q norm of 0.90, 100, 15. So we get x equals 119.2233. Then the other method is finding first the z-score. So you enter only the area, nothing else. So you get the z-score is 1.2852. So your value of x is going to be 100, which is the mean, plus the z-score that you just found, times the standard deviation. So you get the same result. So just let me finish copying this information into our notes. So this is going to be 100 plus 128, 50, 52 times 15. So it's going to be 119.2233. So the final answer is, again, we need to round up. So 120 is the 90th percentile for this problem. Okay, so now assignments. So we have only 4 problems. So this is section 7.2 exercise set on page 317. So you're going to solve problems 18, 20, 22, and finally 32. So the first 3 problems is just practicing with the normal distribution, and the last problem is the application. The last problem is the actual problem that resembles the problem that we solved during this section. So let me show you those problems for you if you don't have your book. So first 22, you have first 18. Okay, 18. A normal population has a mean, mu equals 9, and the standard deviation sigma equals 6, and then you need to answer 2 questions. And the same thing for 20 and 22. So let me increase the font size. So problem 18 is there. and 20. Take screenshots. Then we have problem 22 here. Take another screenshot. And finally problem 32 over here. Another screenshot. Submit your screenshots through Canvas by using the submit button in the corresponding class work section.